your boom, boom, boom. Let me get it now.
Boom, boom, boom. Gotta get that boom, boom, boom.
Hello, Guten Tag, and Slay Queen. My name is Chef Russo, and welcome to Cooking in the Lab. Today, we'll be discovering the science behind your favorite dishes. In this fun and enlightening cooking video, we'll explore the fantastic ways physics impacts cooking and how you can apply it in your own kitchen. Now, you might be thinking, there's no way there's physics in stuff I make and bake, which you're wrong! Because there is. Say, for instance, you're at home all by yourself and you were forced to make mac and cheese because your parents didn't bring you home food at 12 o'clock at night because they're out playing bingo? Physics. And especially in the meal we're preparing today, it plays a vital role. Now, drum roll please. The dish we're making today is fried ice. Now, no meal is done without dessert, of course. And so we'll also today go on to bake strawberry almond lazire cookies. Now, you might be thinking, there's no way she's gonna be cooking in this, which, alright, you got me. Now let me change to something more appropriate. Perfect, because don't let
anyone change you.
Alright, and with that, let's get cooking. Alright, now before we begin, let's start by gathering some materials. So first, you'll need a pot.
Smoke weed every day.
Preferably a copper pot. And then next you'll need some ice. Right, now this dish is a fun meal to make for the whole family since it only needs 2 ingredients. Wow, that isn't convenient. I don't know what is. Now, for the fried ice, let's start by placing some ice in the pot, which luckily we already did. Let's start then by turning on some heat.
It's on high.
And yeah, let's put it on a medium to high heat and let's just wait for that ice to turn the water into boil. Alright, so as you can see, our water is starting to have some bubbles in it, which meaning that this fried ice is about to be tasting pretty good pretty soon. But before we can get to the tasting, let's take a closer look at this here pot itself. So this pot has what it's called thermal conductivity, and this ultimately refers to the ability of a given material being able to transfer and conduct heat. So when you want to take a deeper
Hello, how are you? I am under the water. Please help me. Here too much raining.
dive and look at the equation itself, this can be denoted by the symbol K, but it can also be denoted by lambda, which is something we learned back when we learned wavelengths, which is something I paid attention to. Yeah. And the reciprocal of the quantity is known as thermal resistivity. And yeah, and while still looking at thermal conductivity, it is important to note that not all objects share the same thermal conductivity level. So looking at this copper pot, the thermal conductivity of this is W over mk, which compared to the water here in this pot only has 0.6, which ultimately is not a lot. Now let's take an even closer look at the water. When boiling water, thermal energy is transferred from the source of heat to the food through conduction, or in this case, the movement of heat within an object when the stove touches the pot. When a pot of water is placed upon the stove to boil, conduction heat warms up the pot, which then heats the water molecules inside. As the molecules heat, convection causes them to move away from the interior of the pot as they are replaced by cooler molecules. The rate of heat transfer depends solely upon the temperatures of each entity and the medium through which the thermal energy is being transferred. While still looking at the pot, where you now see the ice has turned into water, and it now is boiling, producing steam, the now boiling water shows how the water has reached its heat capacity. This heat capacity is described as the ratio of the absorbed by material to temperature change, which is normally expressed as calories per degree. In terms of actual amount of material being considered most commonly a mole, but if you're trying to be more specific, then the capacity would be in calories per gram called specific heat. Comparing other heat capacities, water tends to have one of the least amount of heat capacity compared to gasoline, rubber, and the Kardashians, also known as plastics. For making our fried ice, we talked about 2 out of the 3 types of heat transfer. We talked about convection and conduction, but it's important to note the third and final type of heat transfer called radiation. Radiation is the heat transferred by the flow of electromagnetic radiation, like heat felt from a campfire. Radiation is the only type of heat transfer that can happen in a vacuum. Another important thing to note is that heat transferred by radiation is invisible to the eye and not affected by airflow. It is also in our daily lives that we feel the warmth from different sources of radiation heat transfer. For example, sunlight, light bulbs, and ovens. With heat transfer, that happens to be one of the 2 ways of transferring energy, one by heat transfer itself and one by doing work. When doing work, energy can be transferred from one object to another by just simply doing work. To do work requires that an agent exert a force on an object over a distance. When work is done, energy is transferred from the agent to the object, which results in change in the object's motion, more specifically, a change in the object's kinetic energy. With that, this concludes my AP Physics subfinal on heat and heat transfer. And this is Shaden Russo signing off. Good ciao.